Good afternoon, students. We had started the module 5 since yesterday. Today we will see the type of coupling. You are already familiar with this capacitive coupling, which is going to produce a DC isolation, and capacitors are going to pass AC. So this we have already seen, so I will not go further into details. But the limitation of this also, you know that at low frequency, the bandwidth is going to be reduced because of this capacitors only. The low frequencies will have X equals 1 over 2 pi Fc, means when F is very low, X is very high, and that is when this coupling capacitance offers lot of reactance to the low frequency signals. That is the problem with the capacitive coupling. Now there is another method called inductive coupling or transformer coupling. Here you know that inductance is going to pass DC and it is going to block AC. XL is equal to 2 pi FL. So in this case, as far as the low frequency is concerned, you will not have any serious issues. Whereas for high frequencies, we will have these issues, as high frequencies are going to be blocked by the inductor. So in one way or the other, we have these issues. But anyhow, in the high frequencies, even the device will have its own issues because of the parasitic capacitances which are inside. Now you can see this capacitive coupling and transformer coupling. Whenever we have to pump a large amount of power to the load, in general they prefer transformer coupling, because transformer is working through the electromagnetic induction. So that is one advantage of transformer coupling. Now this is called direct coupling. In the sense, you can see the output at the collector is directly connected to the base. Generally, operational amplifier internally is a direct coupled amplifier. That means inside the operational amplifier's circuit, inside the integrated circuit, there are no coupling capacitors at all. So that is a direct coupled amplifier. So whatever changes happen here at the collector of the first transistor, they get reflected at the base. But the point here is, when the signal is not present here, the DC is also present here. You can see. In the case of the first one, in the case of capacitive coupling, the collector's DC will not be transferred to the next stage. But here the collector DC is also transferred to the next stage. So accordingly, the next stage's biasing or the next stage's design is more critical. For example, let us say here at the collector it is supposed to be VCC by 2. Now this is at VCC by 2. Now this emitter cannot be directly grounded. The second transistor's emitter cannot be directly grounded. The reason is, if this is VCC by 2, then naturally this transistor will go into saturation. But inside an amplifier, we want all the transistors to be working in active region. So that is where, when we have direct coupling, the low frequency cutoff is not actually there, because right from 0 Hertz to higher frequencies, there is a direct coupling of the signals from the collector to the base. So whatever effect this coupling capacitor was happening, that will not be there. So in the case of direct coupled amplifiers, there is no lower cutoff frequency at all. That is the point. But the point to be taken into consideration is that this DC, which is VCC by 2, that VCC by 2 is going to drive the base of the second transistor. Now the second transistor should not be allowed to saturate. So if it should not be allowed to saturate, even at the emitter, there must be one more resistance, so that VBE will be lesser, transistor will be prevented to get into saturation. That way the design of an operational amplifier or the design of a direct coupled amplifier is more critical or more difficult when compared to the normal capacitive coupled or inductive coupled amplifiers. Let me proceed. Now we will discuss one more thing or one more method of classification by means of which the amplifiers can be classified. It is called class A, class AB, class B and class C. You can see in the first case, the positive cycle as well as the negative cycle both are intact. In the sense, the device which is used inside the amplifier, that is going to work for both the cycles. Till now, whatever amplifiers we have seen, they all come under class A only. But we did not discuss them as power amplifiers till now. We have been always discussing about the base current being in the milliamperes range. So, till now, till module 4, whatever amplifiers we were discussing, they were all handling power only in the milliwatt range. Whenever we have amplifiers which are working in the wattage range, either in watts or in kilowatts, they are going to be power amplifiers. They will have both voltage gain as well as current gain. So, even in power amplifiers, there can be class A, in the sense, the device is going to conduct both in the positive cycle as well as in the negative cycle, which was the case earlier also. Now, the point is, when the device is conducting in both cycles, the amplifier is going to consume DC power also in both cycles. That means the transistor is remaining in the active region, that is in the middle of the load line. So, it is going to consume DC power. For example, imagine, let me write that amplifier's diagram here. This amplifier is powered by, let us say this is plus 12 volts and the other end is ground. So, the collector of the BJT will be kept at 6 volts, kept at plus 6 volts now. Now, you will have to visualize inside this amplifier there is a resistor at the collector and the collector is at 6 volts. That means there is a resistor RC. Now, across RC there is 6 volts. Even if you consider the voltage divider bias also, the emitter resistance is much lesser. When the emitter resistance is much lesser, let us consider only the collector resistance. Across collector there is 6 volts. Let us imagine a current of 1 milliampere. If we imagine a current of 1 milliampere, across this RC there will be a power dissipation of 6 milliwatt. Now, this power 6 milliwatt will always be there across the resistor because the transistor is conducting, and in the active region where we say ICQ is 1 milliampere. Take for example. Now, this we say is a static power dissipation, in the sense whether the AC signal is present or not, the amplifier is powered by DC and this is called as static power dissipation. When AC signal is applied, what is going to happen? When AC signal is applied, it is going to work this way. Let me write it clearly. When AC signal is applied, it is going to work this way, if it is a common emitter amplifier. Again, it is going from VCC to ground at that time. But when AC signal is not applied, still it is consuming power. You can see here. Let me remove this now. Let me remove the signal itself because we are discussing only DC. So now you can see across this collector resistance 6 volts is there, and because of which across the resistance 6 milliwatt power is going to be dissipated, which is the total wastage of power. What we want is, when the input signal is absent, the circuit should not draw any power. That is what we ideally want. But now we have, even when the input signal is absent, now we have the power consumption in the amplifier. Now, why it is called as static power? Because even when the signal is absent, the circuit is drawing power. That is what is called as static power consumption. When the signal is present, if it is drawing power, then we call it as dynamic power consumption. Now you can see 6 milliwatt is always present here. Now, think about power amplifier. Let me remove this. Think about power amplifier where the same power amplifier, let us say the current is, I'll write it as ICQ equals 1 ampere. Instead of 1 milliampere, let us say it is 1 ampere. If the quiescent current of the transistor is 1 ampere, because now we are dealing with power amplifiers which will work with watts. Now for the same collector resistance, 1 ampere into 6 volts is 6 watts. 6 watts of power being wasted in the quiescent conditions when the signal is absent also. Now, whether the AC signal is present or not, transistor is working in the active region only. Across the transistor also, this wattage will be there. Across the resistor also, this wattage will be there. Means what? Across the resistor, 6 volts is there. 6 volts into 1 ampere is 6 watts. Across the transistor, the remaining 6 volts is there. Current is same, 1 ampere. So, across the transistor also 6 watts is there. Gradually transistor will heat up because there is a static power and the life of the transistor will be reduced because of the continuous static power. That is why in such case we have to use additional heat sinks where the heat of the transistor is being dissipated into the atmosphere and the transistor life can be somewhat increased. Now I hope you can understand the problem with the class A amplifier when we have power amplifiers. Till now we were discussing only the pre-amplifiers, that means the amplifiers which were working with the milliampere or milliwatt range, there we could ignore the power consumption. Now in this case, when there is a quiescent power of 6 watts always, we cannot ignore this because the transistor's life is going to be reduced. We should have additional precautions like heat sinks. Even if you connect heat sinks also, then even then the power consumption will always be there. Wastage of power will always be there when the input signal is not at all present. For example, imagine the amplifier is turned on for a public function and the mic set is connected, but the speaker has not yet come on stage, speaker is not yet speaking. When the speaker is not yet speaking, still the amplifier is on. We have a power amplifier which has to be class A only, means it has to work with both the cycles of the signal. When we speak, we will always end up with this type of signal. Why? When we speak, the vocal cords vibrate up and down. And the vocal cords vibrate up and down, the vocal cords are going to produce a pressure on the diaphragm of the microphone, which is to and fro. Because right now when I am speaking, air is going out of my mouth. From the throat, air is coming up. And when the air is coming up, I am modulating the air flow through my vocal cords. And my throat is involved in producing vowels and my mouth is involved in producing consonants using the lips or using the teeth or using the tongue itself. So that way when the speech is coming out, speech is subjected to continuous air pressure. That air pressure hits the diaphragm inside the microphone. And inside the microphone, again there is a small transistor only and the microphone is powered by a DC supply. And whenever the diaphragm vibrates as per the air pressure, the sound gets produced, the sound gets converted into the electrical form with the microphone. And that sound will have the positive cycle also, negative cycle also. Actually, we cannot say it as positive cycle or negative cycle. We should say it as upper wave or lower wave or front wave or back wave or the to and fro movement of the air column itself. You already know that sound travels only through the air medium. Sound cannot travel in vacuum. So it is basically the air molecules moving front and back because of the pressure produced at the vocal cords. Students are listening to song also and attending to class also. Anyway, anyway in the module 5, I am going to end the syllabus in the next few classes. Later on, it is your own effort to clear the tests and to clear the exams. So, I was discussing about this class A operation. In general, audio amplifiers have to be of class A, because when I speak, the speech waveform is going to be having this to and fro movement or up and down movement, or in general it is a omnidirectional movement. It is a three-dimensional movement. Now this signal has to be completely amplified by the amplifier in case of a function, let us say in case of a public function. Now imagine the public function has not yet commenced, amplifier is turned on by the electrician or by the organizers. The speaker has not yet arrived on stage, imagine, amplifier box is still on, and at that time also it is going to draw power. Here I am talking about the quiescent condition of 1 ampere and the amplifier working in that way. Now it will keep on drawing 6 watts of power always. But in case of a public function, it has to be that way because the complete waveform has to be amplified. So we have to compromise on the amplifiers, devices, life only as such. It will have a lesser life. In the long run, amplifier will not sustain because there is a DC power consumption always. That is called class A operation. Class A means the amplifier works through the complete cycle of the input signal. Now, how to reduce the power consumption? If you have to reduce the power consumption, we can compromise on quality now. You can see the second picture here. In the second figure, the amplifier is going to work in the complete full cycle, positive cycle. It is shown in red color. But in the negative cycle, let us say it is not working. For example, in the first case of class A, it is working for the complete 360-degree cycle. Now, in the second case called class AB, it is class AB, you can see that out of 360-degree, for the shaded portion, the amplifier is not working. Imagine that way. How do we make it not to work that way? That we will see later on. We will have such biasing circuits, by means of which we will prevent the transistor to work during this shaded portion. Now, in this case, the device is not working for the complete 360-degree cycle. It is working here. For the 180-degree cycle, it is working. Then it is working here. Then it is working here. In this region, it is not working. The amplifier is not working. Means the amplifier is working in between 180 and 360. Let me admit a student. The amplifier is working in between 180 and 360. In the first case, it is working in both cycles, means total 360-degree, the device is working. In the second case, we want to save some power. When we want to save some power, we will make it work for a lesser duration. But now, we will be losing out this, right? We will be losing out this waveform. We will lose out because we are making a compromise in quality. Now, definitely audio amplifier cannot be class AB. Audio amplifier has to be class A only. But we can use this class AB in some other applications where audio signal is not there. There are many such applications in power electronics where the complete cycle of the AC waveform is not required. In the sense, for example, let us say you have your electrical fan working at home, electric fan working. Electric fan requires more power only when you switch it on to overcome the inertia in the beginning. Later on, when the fan starts rotating, the same power need not be required because it is already rotating. Later on, it has to keep rotating, only that much of power can be enough. But in general, what we do is we keep on feeding that power later on also, and that is when the fan heats up. But there are other applications where the complete cycle is not required. We initiate it, and again in the next cycle, again one positive cycle is going to come. So for this much portion, if the fan is not working, fan will not stop abruptly, because again the next cycle is going to come here. When the next cycle is going to come here, the fan keeps on rotating. That way, in the applications of power electronics, we can go for class AB operation. Now, coming to the class B operation, only in the one cycle, in the positive cycle, amplifier is working. In the complete negative cycle, amplifier is not at all working, which means we are going to save 50% power here in the case of class B. You can see that. Let us say class A is consuming 6 watts of power. If the same amplifier is made as class B by means of a proper biasing, so that in the negative cycle, transistor will completely turn off. In the negative cycle, if the transistor completely turns off, now the circuit is consuming power only for positive cycle. That means that 6 watts power is consumed only during positive cycle, not during negative cycle. Now, if at all we measure energy, how do we measure energy? In terms of kilowatt hour. So, let us say the amplifier is working for 1 hour. If it is working for 1 hour, now that corresponds to, it is consuming 6 watts, and that is 6 watt hour. For 1 hour, it keeps consuming this much of energy. Now, in the case of class B, it can be reduced to 3 watt hour. Even though it is consuming 6 watts normally here, but in this negative cycle, the device is off. It is in the cutoff region. In the cutoff region, no power is consumed. When there is no power consumed, 50% power is reduced here. So, if we take 1 hour there, it is not 6 watt hour, it is now 3 watt hour. That way, we save 50% power in the case of class B operation. But what is the disadvantage there? The disadvantage is that half of the signal is gone. Half of the signal, even if it is gone, the equipment may keep still working. I gave an example of electric fan. In the case of electric fan, if at all we use a class B amplifier, fan will keep working, because in the next cycle anyhow, the next cycle is going to come. Fan will keep working after some time. Only thing is, in the beginning, it may be difficult for the transistor to reach to the full speed, because in the beginning only one cycle is present from the beginning. So, depending upon the application, we can use class B amplifier. Now, coming lastly to class C amplifier. You can see in the class C amplifier that even in the positive cycle also, it is not working even for 180 degree. You can see here in class A, it is complete 360 degree. In class AB, it is between 180 to 360. In class B, it is exactly 180. In class C, it is less than 180. You can see it is not working here, and it is not working here also. It is not working here, and it is not working here also. It is working only here, which means the total angle up to which the device is working is only less than 180 degree. That is called class C. Now, here we lose maximum quality of the input waveform, but we are saving a lot of power now. Even though we lose quality of the waveform, we can save a lot of power. Now, you may think, what is the point of saving power when we are losing the waveform? Now, if the circuit can have some arrangement by means of which this signal wave shape which is lost in the amplifier, if it can be reconstructed in some other way, then power is also saved, but the shape of the waveform may not be exactly sine wave. I am telling you an example where, let us say, amplifier is amplifying only this portion, only this much portion. Okay, and let me change the color. This portion is gone. Let us say this portion is gone, this portion is gone. Only this much portion is there. That means out of 360 degree cycle, less than 180 degree, only this much is there. Now, the wave shape is completely gone. When the wave shape is completely gone, definitely this cannot be audio amplifier, because there is a signal quality problem in the case of class C fully. There is a quality problem even with class AB and with class B also, but in class C there is minimum quality because only a portion of the waveform is present at the output. But in some applications, the shape of the waveform is not important. For example, in radio frequency applications, the shape is not important. Now, when you are using your mobile phone, your voice has to reach to the other person with whom you are talking. So, there is an audio amplifier. The audio amplifier has to be class A only. There is no other choice. But that speech is going on a radio carrier of 2.4 gigahertz or 2400 megahertz. Now, the 2.4 gigahertz is going to reach to another mobile phone, and the 2.4 gigahertz is working as a carrier frequency. Now, the carrier frequency's shape is not important. Why? Because carrier is carrying the information signal. Information signal is your voice. Information signal's quality is important, but the carrier's voice is not important. So, in case of an RF amplifier or a radio amplifier, when the carrier wave signal shape is not actually important, we can use class C amplifier there. Advantage is what? In class C amplifier, we save lot of power. RF power is very expensive in the sense, if an amplifier has to work at 2.4 gigahertz, it is quite expensive. So, we can save the power there. That is how your mobile phone also can save some power from the battery. So, remember, all audio amplifiers are class A, all radio amplifiers are class C. Class AB and class B can be utilized in other applications such as power electronics applications. Whereas in electronics, regular electronics and communication applications, always all audio amplifiers are class A, all radio amplifiers are class C. Even though in the case of class C, even if the waveform is distorted amplitude wise, it can somehow be reconstructed in some other way at the receiver. That techniques we will see later on. There are techniques to recover the shape of the waveform at the receiver. We will see that techniques when we discuss class C amplifiers circuit. To give you one more example, when you travel in a bus is carrying you to your destination, it is not the shape of the bus that is important. It is the efficiency of the bus, it is the way in which driver takes you all the way to the destination safely and bus carries you without any lot of jerk or disturbance. So, the engine performance of the bus is important. It is not the shape of the bus that is important, right? The vehicle's shape or appearance is not important. The vehicle's efficiency and comfort of traveling is important. The vehicle is a carrier for you. Inside the vehicle, your shape is important for you, right? You should not be deformed when you are traveling inside a bus or a car. That way, the carrier which is carrying you, it may be train, it may be bus, it may be flight, it may be car, it may be bike. Its shape is not important, but your shape is important. Same way, you are like an information signal. Your bike or car or train or bus or flight is basically a carrier. In the same way, as the carrier's wave shape is not important for us, only the information signal's shape is important for us. Now, the radio amplifier is going to carry the voice information. The voice information is amplified by an audio amplifier. Audio amplifier has to be class A. Radio amplifier can be class C. That is how we save power in the case of class C amplifier. So, in this way, based on the angle at which the device is going to work, Based on that, we are classifying the amplifiers into 4 categories. You can see this is class A, where this is the input signal and this is the input characteristic curve, VBE versus IB of the transistor. Now you know that this is the characteristic curve where we are using this transistor in the middle. So this midpoint, that is the Q point. Here in the picture it is shown not with the output curve but with the input curve. So Q point comes somewhere in the middle. So class A bias point on linear portion of the curve. Now you can see when the input signal is fed to the base, output signal is produced at the collector, and you can see that wave shape has retained. Undistorted base current waveform is happening because of the linear operation of the transistor, because the Q point is at the middle. Now this is class A. Let me go to the next slide. Now this is class AB, where you can see Q point is fixed here now. Earlier Q point was in the middle in the linear curve. Now the Q point is fixed somewhere nearer to the cutoff. Class AB bias point just above cutoff. Now you can see when we apply this waveform, you can see here it is cutoff region where transistor is not at all on. When the transistor is not at all on, that waveform is gone. You can see here that portion of the waveform is gone. Now you already know in a common emitter amplifier there is a 180-degree phase shift. So you can correspond the input with the output. This is the input signal which is having a complete 360 degree, but in the output you can see positive cycle has come, negative cycle is gone partly. You can see here for this much portion transistor is working. For the shaded portion transistor is not working because it is in the cutoff region there. Q point is purposefully shifted nearer to cutoff region. So the wave shape is having distortion. Slightly over half cycles conduction is happening. This is class AB. Here the waveform is distorted, but if it is used for any AC power line application in power electronics for driving any electrical equipment such as fan, now we can use class EAB there, provided we are saving that much of power there. This is now class EAB. Coming to class B, now you can see here the Q point is very much nearer to 0. Class B bias point is at 0 volts. So the negative cycle BJT will not conduct at all. Now in the positive cycle also until it crosses 0.7 volts, because still transistor is in the cutoff region only. Until the base to emitter voltage goes beyond 0.7 volts, transistor will not turn on. Now above which only transistor is turning on. So this we can say class B. If we have to make it exactly class B, we can give about 0.7 volts in the beginning itself. Instead of fixing it exactly at 0 volts, we can give a bias voltage to the base so that it will completely turn on at the positive cycle. It will remain off in the negative cycle. Now that is class B, half cycles only and distorted near cutoff. It is distorted near cutoff because here even that 0.7 volts is also not there. This is class B. Lastly, coming to class C, you can see that the transistor's Q point is beyond 0 volts. Q point is now at a negative voltage. That means base is given with the negative voltage now initially. Now you can see in the negative cycle transistor is completely off. Now in the positive cycle, only when it reaches beyond 0.7, then it is turning on. So you can see only till here. Till here transistor is completely off. After that only transistor is turning on, because the bias point itself is below cutoff. So in such a case only pulses of VB input voltage are produced, that is only this much portion is produced. Upper portion of the positive cycle will be produced in case of a normal amplifier without phase shift. If it is with phase shift, it is the negative cycles upper portion going to be produced. Now this is class C, where for majority of the input signal transistor is off. Now I told you this is useful for RF amplifiers where only a small portion of the radio frequency is coming. The lost portion of the radio frequency can be reconstructed or it can be produced in some other way using tuning circuits such as inductances and capacitances. We will discuss that when we discuss the circuit of the class C amplifier. So through these diagrams now it is clearer to you about how class A, AB, B and C are going to work. And remember, all these are power amplifiers. In the sense, all these amplifiers handle power in watts and not in milliwatts. So an amplifier summary here. You can see the complete summary in the table. Class A, complete 360 degree cycle. Class AB, in between 180 degree and 360 degree. Class B, only for 180 degree. Class C is less than 180 degree. There is one more amplifier called class D that is going to have a pulse operation. I am going to discuss about class D amplifier later on. In fact, all your mobile chargers and your SMPS circuits inside desktop computers or inside television sets, they all work through class D operation. I will tell that later on. So in case of class A, the quiescent point is VCEQ is equal to VCC by 2 and ICQ equals IC sat by 2. And the operating region is the mid-active region in the middle of the load line. I will discuss the last column later on. Now the quiescent point of class AB operation, VCEQ is greater than VCC by 2. Why? The transistor is very much nearer to the cutoff region. You know that when the transistor is nearer to the cutoff region, collector voltage will be nearing to the supply voltage itself. So VCEQ is greater than VCC by 2 and ICQ is less than IC sat by 2 because transistor is nearer to cutoff region. Now in the case of class B, VCEQ equals VCC and VEE, ICQ is 0. In the case of class B, when the signal is absent, transistor is not working at all, or when the signal is present also, only to one cycle it is working, to the other cycle it is not working. That way the quiescent point will be either VCC and VEE if we have push-pull operation. I am going to talk about push-pull operation later on when we use PNP and NPN together. So as of now, understand that the quiescent current is 0 because the transistor is completely off. So the Q point is at cutoff region only. Coming to class C operation, VCEQ is VCC because transistor is completely off. ICQ is also 0. There is no push-pull in this case. In case of class B, there can be a push-pull operation, one PNP, one NPN. In the case of class C, there is no push-pull operation. It is used for radio amplification. And in the case of class C, operating region is below cutoff as I had shown you previously in the diagram. Now class D is a pulse operation where it is a high speed switching. It is called as PWM, pulse width modulation. Let me not talk about PWM now. When I discuss the block diagram of the class D amplifier, at that time let me tell you. That is at the end of this module. Now in case of class D, the transistor will be working only between saturation and cutoff. It will not be in active region. It is working like a switch only. So you can see here, as class A is working for complete 360 degree cycle, the efficiency is only 25 to 50%. Efficiency means the power which we provide to the amplifier and the power which is utilized by the amplifier. For example, output power divided by input power. In the case of all these amplifiers, output power is AC, whereas input power is DC. How is it so? It is so because we are giving biasing supply to the amplifier, supply voltage is DC, and there is a quiescent current ICQ that is also DC. So, input to the amplifier is not the input signal's power. Please understand, in the case of power amplifiers, input power to the amplifier is not the input signal's power. Input signal will always be weak only in nature. Here input power means the power which we are supplying to the amplifier, that is DC power. And the output power is actually the AC power. Input signal gets amplified by the amplifier, that is AC power. So the efficiency is output power by input power or AC power by DC power. Later on we will have exercises to understand about the efficiency. So in the case of class A, efficiency is only 25 to 50%. In the case of class AB, it is 50 to 78.5%. In the case of class B, it is less than or equal to 78.5%. We have a derivation for this value. How we get this 78.5%, we will see that later on. In the case of class C, it is 78.5 till 90%. In the case of class D, it is more than 90%. See, the efficiency of class D is more than 90%. That way, the efficiency of your mobile phone chargers or the efficiency of the SMPS circuits inside the desktop computers or the SMPS circuits which are inside the television sets, they are all having efficiency more than 90%. You can observe this directly. When your mobile phone is charging, you can check which one is heating up, whether the charger is heating up or whether the mobile phone is heating up. Partly both will be heating up, but more heat will be nearer to the mobile phone only because the battery is charging there. Inside the charger, it is a class D operation happening. It is only between saturation and cutoff. There is no active region there. So there is no dissipation of power in the middle of the load line. So due to which efficiency of class D amplifier is more than 90%. That is how nowadays we have very compact televisions, compact desktop computers, compact mobile phone chargers also. Why? Inside all these equipments we are using class D operation where efficiency is really very high. So whenever efficiency is very low, what happens? The remaining power gets wasted as heat only. Now, if that heat can be reduced, efficiency is increased and even the life of the equipment also is going to be increased. That is the idea here. But we cannot use class D operation for our RF amplifier. You may think that because it is greater than 90%, can we use it for our radio frequency amplifier also? That is not possible because in the case of radio frequency amplifier, we require at least some shape of the carrier wave, right? Some portion of the carrier wave needs to be retained because using that only we are going to construct the remaining portion. But in the case of class D operation, it is simply a switching. We will see that later on when we discuss the circuit diagrams and block diagrams. So now, coming to the last point. There are two load lines. I don't know, I may not be able to finish this now, but still let me start. There are two load lines. There is something called DC load line with respect to the DC equivalent circuit, and there is AC load line with respect to the AC equivalent circuit. But the Q point is the same with both of them. You have already seen how to plot a DC load line, right? When the transistor is completely in the cutoff region, the point is identified in the x-axis where it is corresponding to VCC. When the transistor is completely on, the point is identified in the y-axis, that is VCC divided by RC, that is IC sat, saturation current of the transistor. When you join those 2 points, you will have a DC load line, and we set our ideal quiescent point in the middle of the DC load line where it corresponds to VCC by 2 and IC sat by 2. That is DC load line. Now, we have seen how to write a AC equivalent circuit for an amplifier, right? Considering the AC ground, shorting all the capacitors, we are going to write, we have written already AC equivalent circuits for the amplifiers. Now, with respect to AC equivalent circuit, Can we have a load line now? Because with respect to AC equivalent circuit, we will have input there, we will have output there. Can we plot a load line? We can plot a load line. I am going to show you later on how to plot a load line. Now that is called AC load line. But the Q point is the same with both of them. Now you may think why AC load line is required when we had DC load line and we worked with DC load line earlier. Yes, in our earlier amplifiers, AC load line was not required. Why? Because we were handling only milliwatts of power. But now we have to handle larger amount of power. We have something called distortion here, right? We purposefully have an amplitude distortion in all other classes except for class A. In AB and B and C, we have serious amplitude distortion. Now, when there is amplitude distortion, we want to know what about the AC operation of the amplifier itself, up to what extent it can conduct or not conduct. We are going to analyze the amplifier circuit using AC load line now. Later on, when I show you the examples, it will be more clearer to you. So now we have two load lines called DC load line and AC load line. But the thing is, the Q point is the same with both of them. Quiescent point will remain the same. Only thing is, x-axis and y-axis points where we mark them will be different. We will see how. Now we already know about this circuit. This is a voltage